Okay, lesson 17, as you guys know, was a pretty tough one. There was lots of things going on. We had sine and cosine, and we talked about all of the stretches and compressions and shifts and so on with sine and cosine. Well, now we're going to talk about their reciprocals. So we're going to talk about cotangent, secant, tangent, and also cosecant as well. So let's start out with the basics like we did before, and let's talk about what sine, cosine, and tangent are at particular values to help us graph what tangent is. So I'm going to do a little mini unit circle over here on the right. So if I talk about at t equals 0 or even theta equals 0, the sine value, as you guys know, this is 1, 0. So the sine value is 0, the cosine value is 1. So when I find tangent, we know tangent is the same as sine over cosine, which equals 0 over 1, so I get 0. At pi over 6, right, that's the point root 3 over 2, comma 1/2. So my sine is 1/2, my cosine is root 3 over 2. So when I divide those, I get 1/2 divided by root 3 over 2, which is the same as 1 over root 3, which rationalized to be root 3 over 3. So we'll find that as a decimal. It's around 0.577. Pi over 4 we know is root 2 over 2, comma root 2 over 2. So its tangent value is very easy. We just take the sine divided by cosine, so we get 1. And then pi over 3 is where we go out 1/2. Up root 3 over 2. So when we divide those out, we get root 3, which is approximately 1.732. And then pi over 2 is the point 0, comma 1. So 1 for sine, 0 for cosine. So when I do 1 divided by 0, I get undefined. So the tangent function will not be at what we call a continuous function. It's not like sine and cosine where I could draw them without lifting my pencil. Instead, it's going to be something where we have points that are undefined. So it's going to have asymptotes. So at pi over 2, and also down here at negative pi over 2, or you might call it 3 pi over 2. In all of these locations, the tangent value is undefined. So what that is an asymptote. So we're going to draw these vertical asymptotes in. Okay, but when t or theta was equal to 0, we had tangent was 0. When we were at pi over 4, we were at a height of 1. But when I got bigger than pi over 4, when I went to pi over 3, I got bigger than 1. I went to 1.732, so around here. And when I was smaller than pi over 4, like at pi over 6, I was like 0.57. So it's kind of sketching out part of this graph for us. And if you check it on your calculator, what this graph ends up looking like, it's kind of like x cubed. It's just repeated every pi. So the period is pi. And it's going to go through the x-axis at pi over 4. If I add pi to it, it's going to be 5 pi over 4. If I add another pi, it's going to be 9 pi over 4, and so on. Okay, so this sketch is pretty simple. It looks like the x cubed function. There's just asymptotes every distance of pi. So our period, as I mentioned, is equal to pi, not 2 pi. And that makes sense if you think about the unit circle, right? We know at pi over 4 the tangent's equal to 1. Well, where is tangent equal to 1? Also over here, right? Because that's negative root 2 over 2, comma negative root 2 over 2. So when we divide them out, we still get positive 1. So like if I have this point right here, its tangent value is repeated when it's down there. So everything is symmetric along the unit circle. It's just across the unit circle. So it's a period of pi. So the domain of tangent ends up being everything except those vertical asymptotes. Okay, so the domain ends up being all real numbers except we're going to say t equals all like pi over 2, and then we said if we add pi to it, right? So looking at it, so if I add pi, I would have this one, which is 3 pi over 2, and so on. Okay, so we're going to say pi over 2, and we're not going to list out all of them, but we're going to use that same notation we used before, pi over 2 plus pi k, where k is an integer. And the range of the tangent function, well, if you talk about all the y values on the tangent function, it goes up forever. Okay, so the y values are actually negative infinity to infinity. We could write it that way, or you could say all real numbers. And the period of the tangent function, like I said, was pi. So tangent of t is equal to tangent of t plus pi or t minus pi or whatever you want to write. Okay. So it says state all the values for t for which tangent is equal to 1. So I just kind of talked about one of those where tangent was equal to 1. So it was here at pi over 4. And the other location was pi away from it. So if I add pi, I get to its other tangent value where the tangent is equal to 1, which is 5 pi over 4. Okay, so it's going to be pi over 4. You're going to have 5 pi over 4, 9 pi over 4. So we write pi over 4 plus pi k. So instead of doing 2 pi k like we did for sine and cosine, because the period was 2 pi, we just do pi k for tangent. Okay, so we get to the graph sketching, and it happens pretty quickly. Okay, so we learned what tangent looks like, so now we need to know how to change it around, right? So as we notice, we have two horizontal transformations. So we have to do the thing where we pull out that 1/3. So when we do that, we have t minus pi over 2. So we just divided by 3, right? Okay, so that's h of t. It's not really divided by 3. We're pulling out the 1/3, dividing by 1/3, I guess I should say. All right, so now what we have is the first transformation is we're going to move right pi over 2. And the second transformation is that we're going to have a horizontal, and since it's 1/3, we do the opposite, so horizontal stretch by 3. Okay, and this really isn't going to do too much. It does adjust the period that we have. So our period was usually pi, but now we're going to divide by 1 over 3, which is the same as multiplying by 3. So our period is now 3 pi. So that makes sense, a horizontal stretch by 3. If our period was pi before, it's now going to be 3 pi. Okay, and we're also going to move to the right pi over 2. So the important point, looking back at our graph, is what I call the starting point right there. So we're going to graph that starting point, shifted over to the right pi over 2. So we're going to go over to pi over 2. And that's going to be my starting point. And then the period is 3 pi. So what that means is that this starting point, I'm going to go to the left and to the right by 1.5 pi. So 3 over 2 pi and negative 3 over 2 pi. So let's think about what that creates. If I add 3 over 2 pi, that puts me at 4 over 2 pi, which is going to be 2 pi. Let's get rid of those. And if I subtract 3 over 2 pi, I'm at negative pi. And that's going to be the location of my first asymptotes. And then really everything else is the same. It still looks like the cubic function like that. But you might want to draw another full cycle just so you can tell it's the tangent function and there are those asymptotes. So if I add over 3 pi, I'm going to be at 5 pi. And directly between them, right, would be adding 1.5 pi, so adding 3 over 2 pi. So if I do 3 over 2 plus 2 pi, which is 4 over 2, I would get 7 over 2. So this point right here is going to be at 7 over 2 pi. Okay, and usually I'll say graph at least 2 full periods. And remember, I know your Math Excel, you have lots of multiple choice, but your tests, you will actually have to know how to draw these. I know it's difficult, but just one step at a time, right? Okay, so trigonometric functions are called odd or even based on their symmetry. So this goes back to, just basic functions. So if I talk about the most basic odd function is x cubed. Okay, so I want to keep you guys to kind of keep that in the back of your mind. And the most basic even function is going to be x squared. So function f is said to be even if f of negative x equals f of x for every x in the domain. The graph of an even function is symmetric across the y-axis. So if you look at y equals x squared, and you think about folding it over on itself, it folds perfectly across that axis. Okay? And then if we have f of x equals negative f of x, that's going to be an odd function. And the graph of an odd function, it's not symmetric across the x or the y-axis. What happens with an odd function, it's kind of a weird one. I don't know if I can rotate this at all. That's a good thing I could rotate it. But it basically, if you, oh, there, maybe, where did it go? If you flip it over, oops, now I'm really messing it up. If you flip it over like this, it becomes the same function. So do you guys see, like it was y equals x cubed, and when I rotate it 180 degrees, I get exactly the same function. Okay, so that's what it means to be an odd function. So it's kind of strange. Let me scoot this back up a little bit. All right, so the graph of an odd function is, we sometimes say symmetric across the origin, which I'll write here. But I always think when textbooks write it as symmetric across the origin, it's very confusing because students don't really understand what that means. So I'm going to say it's a rotation of 180 degrees. So if you rotate it 180 degrees, you get exactly the same graph. So what we mean by even and odd is, you know, based on the y equals x squared, if I plug in like 2, I get 4 in y equals x squared. If I plug in negative 2, I also get 4. So that's what it's saying. It's saying no matter if you're plugging in the positive version or the negative version of a number, you're going to get the same y value. But this one's saying, oops, this should say f of negative x. I have a typo there. So if I plug in negative 2, I get negative 8. If I plug in positive 2, I had positive 8. Okay, so there are opposite y values in the end. So that should say f of negative x. Sorry about that. All right. So it says sketch the graphs of cosine, sine, and tangent below. Which of them are odd and which of them are even? So if I have cosine, we know cosine starts at 0, 1. And it does the thing where it goes down and back up. So that's cosine. Sine starts at 0, 0. It makes that full turn there, and then back this way. And then we just learned what tangent does. We said tangent goes up, and then it repeats, right, across those asymptotes. Okay, so we make a decision. So cosine is going to be even, because if I plug in any value, like think about pi over 4, if I plug in negative pi over 4, I get the same cosine value. But sine, if I plug in pi over 4 and negative pi over 4, even when I think about it on the unit circle, right, if I plug in pi over 4 and negative pi over 4, I get opposite sign values out. One of them's positive, one's negative. So this is odd. And then if I have tangent, tangent is also odd. Okay, and you can think of it, if you plug in pi over 4 and negative pi over 4, you get opposite. You would also think of rotating. So if you rotate either sine or tangent 180 degrees, so you can even take your paper and turn it upside down, you get exactly the same graph. Okay, so we know that sine and cosecant are reciprocals. Therefore, cosecant is not defined whenever its denominator is equal to 0. So whenever sine of t equals 0. So let me write that out. So sine, well, let me say cosecant. So I'm going to say cosecant of t is equal to 1 over sine of t. So this is equal to 0 when t equals pi, 2 pi, 0, negative pi, and so on. Okay, so the domain of the cosecant function is all real numbers except t equals integer multiples of pi. So we're going to say like pi k. Okay, so that would be like 1 pi, 2 pi, 3 pi, or negative 1, negative 2, negative 3, and even 0, right? Another way you can easily write that is t is not equal to pi k, right? Instead of writing all real numbers, you just write t is not equal to pi k. So that means that the graph has vertical asymptotes at every multiple of pi. Okay, so what I'm going to do is I'm going to lightly, not lightly because I have a black marker here, But I'm going to, maybe with a dotted line, I'm going to draw in what sine is. Okay, so sine goes to 2 pi. This was pi, negative 2 pi. Okay? And every time I cross the x-axis, that's where cosecant is going to have an asymptote. Okay, so it's going to have asymptotes at all of those integer multiples of pi. Well, every other value is going to be a reciprocal, right? So we know sine is equal to 1 at pi over 2, right? It was right here. That's when it was at a height of 1 at pi over 2. Well, when I do 1 over 1, right, I still get 1. So if I take the reciprocal, 1 over 1, that's still 1. So cosecant has that shared value. But maybe I have something over here. So at pi over 6, right, sine of pi over 6 is equal to 1/2. So 1 divided by 1/2, well, that's 2. So instead of being right here, we're going to be up here. And the same thing over here. And as we get closer to the x-axis, so as I'm going this way and getting close to the x-axis, I'm getting further away from the x-axis for the reciprocal. So it makes like a little parabola shape there. And then the same thing happens down here. The reciprocal of -1 is -1. The reciprocal of -1/2 is -2. So it bounces away as well. So it's kind of like you use the sine curve to kind of show you where the max and mins of those parabolas are, and then it bounces away from the sine curve. Okay, it has to be the reciprocal. So that's what cosecant looks like. So it's like little U shapes. So little U shapes, and it's going the opposite directions of the sine curve. Okay, so that's cosecant's graph. So y equals cosecant of t. Oh, I guess I graphed it too soon. It's on the other page, right? So what is the range of the cosecant function? So the range of the cosecant function, you would think it would be everything. You know, that's what tangent was, negative infinity to infinity. But we actually don't include any of these values in the middle. Okay? So the smallest, well, it's not really the smallest. I can go to negative infinity. But for the negative numbers, the biggest negative number I have is -1. So it's going to be negative infinity to -1, and it includes -1. And then it skips over all those intermediate numbers. And then it goes from 1 to infinity. And then the period of the cosecant function. So if you look at it, it completes. So this is one part of the curve, the second part of the curve, and then it repeats, right? So your period is still 2 pi, just like sine and cosine. So period is 2 pi. And then it says the same properties are true for the secant function. So again, it's the reciprocal of cosecant. So if you have secant, it's going to be 1 over, did I say cosecant? Cosine. So we're going to have 1 over cosine. Which we know cosine starts at 0, 1. It comes down. It's going to hit its lowest point at pi. And then it's going to go back up, right? Should have done this in a dotted line. Let me do a dotted. So we're coming down, and then we're going to go back up. So always drawing, you know, sine and cosine for these will help. So if you have the reciprocal cosine, then lightly draw in what cosine is. Okay, so just like before, wherever it crosses the x-axis, so wherever cosine is crossing the x-axis, that means that this curve is going to have asymptotes. So secant is going to have asymptotes at those places. So it's not a point actually on the graph. I just was drawing that. Okay, so secant will end up being here. It was a height of 1. 1 over 1 is 1. So it bounces away from the curve. It's never going to cross any part of cosine. So it's bouncing away. So it's just these little U shapes. And that's your curve. Okay, so that's what secant looks like. So obviously it can get pretty complicated when you have stretches, reflections, and so on, your favorite. But we're going to do the exact same thing. Okay, so it says in the last section we knew that tangent was different than sine and cosine. The same is true for cotangent. Its graph is much different from cosecant and secant. It's going to look like tangent basically. It will just be the opposite direction. So cotangent equals 1 over tangent, which would be the reciprocal of, so tangent was sine over cosine, so this ends up being cosine over sine. So it's not defined when sine is equal to 0. So again, there's going to be those asymptotes wherever sine is equal to 0, which is pi, 2 pi, 0, and so on. So we're going to have these asymptotes. So if you remember, tangent had asymptotes at pi over 2, 3 pi over 2, and so on. So it's not quite the same graph, but it's going to be similar. Okay, and then we can think about a couple values. So let's say we're at pi over 2. So if I have cotangent of pi over 2, what that is cosine of pi over 2 over sine of pi over 2. Well, cosine of pi over 2 is 0. Sine of pi over 2 is 1. So we get 0 over 1, which is 0, which is exactly what I think you guys probably thought it was. It crosses right there. So it's right in between each of these asymptotes. It's where it's crossing. And now we make a decision. Does it look the same as tangent like that? And it actually doesn't. It goes the opposite way. It will end up going like a negative x cubed. Okay, and here's why. Let's think about a couple basic ones. I always think of the pi over 4s because tangent and cotangent for pi over 4s are really easy. It's always 1 or negative 1. So if I'm at pi over 4, if I do cosine of pi over 4 over sine of pi over 4, I get 1. But pi over 4 is over here now. Okay? And then same thing for 3 pi over 4. If I do that, cosine over sine, I get negative 1. Right? So it has to go down like this because of that. And you can do it for all the other pi over 4 values, and you'll see that the rest of them go down like that as well. Okay, so that's showing 4 periods right there. Okay, so cotangent ends up being just kind of a reflection of the tangent. So what is the domain of the cotangent function? So if you look at it, it's everything except those integer multiples of pi. So we're going to say t is everything except pi k. So I'll write it like that. Or you could say all real numbers except for t equals pi k. And the range is negative infinity to infinity. Or you could say all real numbers. And the period is pi. So the next one, say, describe the transformations that change the graphs from the parent functions into the graph of the given function. So for h of x equals negative cosecant x, I'm going to have a vertical stretch by 2. But I also have a negative. Okay, a negative is always some kind of reflection. So it's going to be a reflection over the x-axis. Okay, so these are always hard to graph because, you know, in order to draw cosecant, you should draw sine, and then you draw cosecant, and then we have to do the reflection. So this is going to be 3 steps for me. Okay, so I'm gonna lightly draw. So you can draw this very lightly with your pencil. I'm going to lightly draw the reciprocal cosecant, which is sine. So I'm starting with sine. I'm going to draw going up and down like that. Okay, now I draw the asymptotes in. So my asymptotes for cosecant are going to be anywhere where I cross that x-axis. Okay, so at 0, pi, 2 pi, and so on. So cosecant, I'll draw it a little bit darker here. We'll draw our final answer in another color. So this is cosecant. Right, remember how it bounces away from sine. So you're going to draw those first points and then go away from it. And then we have the negative 2. So we're going to stretch it by 2. So I'll draw that in red. So stretching it vertically just kind of stretches it out just a little bit. Nothing really changes too much. Like those starting points are kind of the same. And then the reflection over the x-axis means that it's going to flip over. Now don't just flip it over. It's tempting to draw it here. A lot of students will try to draw it there. It's not there. It's over the x-axis. So it's going to be over here. And then this one's going to be right here. And this, so maybe I should draw this first one down a little bit more. It'll be the same level as the other one, right? And then this one up here goes down here and up here. So the blue is your final answer. So that is -2 cosecant x. Okay, so it's complicated. I know there's a lot of steps. I'm not going to give you a super hard one on your test. I'll probably give you a couple different ones with sine, cosine, tangent, and so on. Maybe one of these with cosecant or secant. But just one step at a time. Okay, so the next one. So I have 3 secant x plus 2. So if I want secant, I should draw cosine first. So cosine starts there, goes up, comes down. That's where we have 2 pi, pi, and the same thing on this side. Are you guys getting to be pros at drawing sines and cosines? Hopefully. Okay, so everywhere we cross the axis, that's where we're going to have an asymptote. So since I cross the x-axis there, I draw a vertical line through that point. Okay. So then on the bumps, we go the opposite direction. We have the reciprocal. Okay. So our transformations for secant, we have 3 times secant x, which means we have a vertical stretch by 3. And then we have a plus 2, so we're going to go up 2. It's going to be hard for my drawing. Wish I could. I think there's some way I can highlight all of this. Oh, fancy. Don't you guys wish you had the same capabilities with your notes? Okay, we're just going to pull it all the way down. Okay, so this was at a level of 1, right? So we want to go up 2. Up here. And we want to stretch it out by a factor of 3. So stretching, so I'll do this with red, just makes it a little bit skinnier, right? Like taffy, you're stretching it up. Okay, and then moving it up to, oops, let me do this in a different color. So moving it up to, we'll put all of the upper ones on that same level. And all of these lower ones, we're at -1, so it's going to go up 1, 2. It's going to be here. Okay, so one step at a time. And that's your final answer. Okay, one last problem. So this next one, so when you have cotangent of x plus pi over 2, that means I'm going to go, whoops, I almost wrote right. I'm going to go left pi over 2. I'm going to have a vertical stretch by 4. And I'm going to reflect over the x-axis. So if you remember when we had cotangent, cotangent is 1 over tangent, and tangent was sine over cosine. So cotangent equals cosine over sine. Okay, so that's an important one. We'll use that a lot. So cosine over sine. So we want to know where sine is equal to 0. Well, sine is equal to 0 at 0, pi, 2 pi, -pi, -2 pi. Okay? So we're going to take that. That's where our normal asymptotes would be for cotangent. But we're moving left pi over 2. So that means I'm actually going to have my asymptotes, instead of starting at 0, I'm going to move it to the left pi over 2. Okay? So then I'm going to have asymptotes in between all of these integer multiples of pi. And cotangent also went downwards, like -x cubed. We're going to stretch it by 4, so it's just going to get stretched out even taller. And there's not really much you can do with that. But we're also going to reflect it over the x-axis. So this one, I'll still draw in black. This is when we, like after we stretched it out, it still kind of has that same shape. It's not really easy stretching these graphs. But there you have those 3. But when we reflect it over the x-axis, It's actually going to look like a tangent. So what's cool about sine and cosine, secant and cosecant, tangent and cotangent, I'm sure you guys were wondering why like secant and cosecant weren't the ones that were reflections over the line, you know, why they weren't, I shouldn't say reflections, why they weren't reciprocals of one another. Everybody always wonders why sine and cosine aren't reciprocals and secant and cosecant aren't reciprocals. But it has to do with the shapes of their graphs. So sine and cosine look the same. Secant and cosecant look the same. Tangent and cotangent kind of look the same. Just one is backwards, right? But they actually, sine and cosine, if you shift them by pi over 2, you shift one of them over pi over 2, they're identical. Same thing here, shifted over pi over 2, the same. Tangent and cotangent are almost the same, except for that reflection as well. So that's what it has to do. These co-functions end up scooching things over a little bit. Okay, so that was the end of section 18. And a little bit easier next time.